All right, guys, here it is. This is where things start to get a little bit interesting. I know you all hate when I say that because in your mind, interesting equals hard. Okay, but we are going to hopefully avoid that with some thorough explanation of what area is in terms of integration and what it means to the application of finding the area. Okay, so the area, we've got this random weird squiggly curve here with the endpoints A and B, okay? That shaded pink area under that curve, that shaded pink region, okay, under that curve from A to B represents the area. Now, if that was just a random square and we knew the side lengths of that square, we could find the area, okay? If we had a triangle and we knew the base and the height, we could find the area of that triangle. Likewise, we know the area of a rectangle, okay? Base times height, which is also, the base is also what we are going to call the width, just for, keep that in mind for later, okay? So width times height is your area of a rectangle, okay? So if we wanted to possibly estimate the area under that weird squiggly curve there, if we drew some rectangles under there, okay, so say we drew some rectangles under this curve, okay, so we're going to do this, and so we're just going to draw this random number of rectangles under the curve there. If we knew how wide each of those rectangles was, if we knew how tall each of those rectangles was, if we added all the areas of those rectangles together, we would get a pretty good, decent-ish approximation of the area under that curve. What we're going to be doing is using the idea that the more rectangles we've got under this curve, okay, so the more rectangles that we have, we're going to actually get a better representation, because the rectangles, the skinnier they are going to fit better under that curve. So obviously, we could spend the rest of our lives finding the area of each one of these 1,000 rectangles and add them all up together, and we would be able to get the area exactly of what's under that curve. Okay, as the number of rectangles under the curve approaches infinity. Okay, so you have an infinite number of rectangles. In fact, these rectangles get to be so they are thinner than that line, which of course, at a certain point, we don't even have the capabilities of finding the width of something as thin as a hair, for example, okay? So that's the concept that we're going to use to find area under a curve that is not a normal geometric shape that we're used to working with, okay? So we would have some very strangely shaped curves here that we can find the area under, as long as we know the formula for the curve and the endpoints, okay? So that's the idea. And in terms of writing it as an antiderivative or an integral, that's what the area formula looks like. So area A is equal to the antiderivative, that's what the squiggle is, from A to B, okay, those are your endpoints of whatever the curve is, okay? All right, so the process that makes this whole thing possible is called summation. So if you guys remember, there's that poster in my room, okay, on the wall that the windows are on. And you've got that symbol there, okay, on that poster. And that is the summation symbol, okay? So I ate some pie, okay? That's the poster we're looking at, okay? That is the summation. In other words, you are adding up whatever it is that follows that summation symbol. For example, right here, we're looking for the sum from 0. That I there is the index, okay? In other words, that is where you're starting, and this is where you're stopping. Start at 0, end at 6, and add up, get the sum of all of those numbers. So I means start at 0. So I would equal 0, I would equal 1, I would equal 2, all the way up to 6. And then you add those numbers together and you will get the sum from 0 to 6 of I. Okay? Likewise, down here, we've got the sum from 1 to 4 of I squared. So we'll replace I with 1, with 2, with 3, with 4, get those values, 1 squared, 2 squared, 3, etc., and then add them all together, okay? That is a very simple representation of how summation works, okay? Now, these formulas are going to be used in finding the exact area under a curve. Very, 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 very important. Write them down. Now, they're in your book, but the book gives you the formulas that are not foiled out, and you've got a bunch of parentheses with n's and n minus 1s and 2n plus 1s, and I foiled them all together to make them easier to use, okay? So I is n squared plus n over 2. Then you've got I squared, I cubed. And then this formula over here is just for the sum from 1 to n of a constant. For example, the sum from 1 to n of 3 would equal 3n. Okay, so that's an example of how the constant summation formula is used and how it's evaluated. Okay, so we're going to use the sum for the I in terms of n to evaluate for n equals 10 and 100. So what we're doing here is basically working through how the summation is going to work for when we have to use it to find area under a curve. Okay, now let's understand what this is. So we are starting from 1 and ending at some random number n, okay? We don't know what it is. So it is an infinite number, okay? So the process would be to factor out that n squared, okay? So when we do that, we're going to say 1 over n squared times the sum from 1 to n of I plus 1. Okay? Now what we do is we can separate, so we would have the sum from 1 to n of I plus the sum from 1 to n of 1, okay? So notice now here, in the first summation, we've got the I. This I has a replacement, and we are going to replace I with n squared plus n over 2, okay? So we will expand. We'll have 1 over n squared, okay? And once we replace the I with its summation formula in terms of n, we drop the summation symbol. So I is n squared plus n over 2. Okay, and actually we need to kind of lose that second parenthesis for now. Okay, and then remember the sum of a constant is going to be the constant times n. So that's just 1 times n. Okay, so here's what we've got so far. Now the process is to distribute the 1 over n squared into everything inside the parentheses. So we will start here, and we will get n squared over 2n squared. Okay, then we'll go out here, plus n over 2n squared. And then we will distribute all the way here to get plus n over n squared. Okay, now we can simplify just like we would in a regular algebra situation. N squared and n squared divide each other away, and we have 1 over 2. Okay, then n takes one of those away, and we have 1 over 2n. And then n takes one of those away, and we have 1 over n. That is the simplification of that summation. Now that we have that formula, we don't need to worry about common denominators. The only thing we are going to do now is plug in first a 10 where you see the n's and add them together and get that sum. And then 100. Replace n with 100, add those up together, and get the sum. Okay, so that is a very quick example of how summation is going to work to help us find area. Okay, you work to break up your formula here, okay, after you pull out the n values, okay, you factor those out, and then you break up your formula and make replacements for whatever powers of I you've got. Okay, so let's investigate that whole process, okay? Before we begin that, we're looking at these two curves, okay? The curve is negative x squared plus 5, okay? So we've got the right-hand approximation over here, and we've got the left-hand approximation over here. Now, the right-handed approximation means that the right side of each one of those rectangles is the side that meets the curve. So this right here is the right side of this triangle, and that's the side that meets the curve. Likewise, here, 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 and here, okay? Now let's look at the other one. The left-hand approximation means that the left side of each one of those triangles is the side that meets the curve. Now, if you look at the differences between these, you can see that in the right-hand approximation, what happens is we've got this area here. I'm coloring it in gray, okay? We've got this area here that is it's lacking some of our area, okay? So because we don't have an area for those gray portions under that curve, that is the lower sum, okay? In other words, if you find the area of each one of these 5 rectangles and add up those areas together, you're going to be less than the area of what's under the curve because you're missing these gray parts right here, okay? Likewise, if we go to the other graph over there on the right, you've got all of this here that I'm coloring gray that is overhanging That is an overestimate. So if we found the area of each one of those rectangles and added them together, we would get an area that is too big because the gray parts overextend the graph. Now, the interesting thing here is, and I am going to color coordinate here, what we are lacking over here on the right, I just colored it in red, okay? What we're lacking right there in the right-hand approximation is exactly what we are over on the right hand, okay? Likewise, what we are under right here on the left side, the right-hand approximation, is exactly what we are over in the left-hand approximation. Right here, same thing. Coloring it in yellow. What we're lacking here, what we're under in the right-hand approximation is exactly equal to what we're over in the left-hand approximation. So if you did not discern from that information right there, that if you add the lower sum and the upper sum together and divide it by 2, you will get the exact area under that curve, okay? Thankfully, we don't need to do that. We don't need to find the lower sum and then the upper sum in order to get the exact area. We don't need to do that. That's what our summation formulas are going to have. That alleviates that problem, okay? So, one thing I want you to make a very intentional note of. The right-hand approximation is not always the lower sum, okay? The left-hand approximation is not always the upper sum. It all depends on what the curve looks like, okay? The only thing you need to remember is the overestimate, in other words, where the height overextends the curve, that is going to be the upper sum, okay? Doesn't matter. It's not always going to be the left. It's not always going to be the right. It all depends on the curve. Okay. So, here we go. We are going to look at, without using the summation, how to find the right-hand approximation and the left-hand approximation by using the area of each one of these rectangles and adding them up. Okay? So, if we look, our bounds are from 0 to 2, okay? They're from 0 to 2, and the number of rectangles we have under the curve is 5, okay? And that information, it's the exact same graph, okay? But one is a lower sum and the other one is an upper sum, okay? So the width of each one of those rectangles is going to be found by subtracting the higher end point minus the lower over the n value, okay? So that formula would be b minus a all over n. Okay, that's the formula that is going to carry us through when we do use summation in just a few minutes, okay? So once we find the width of all of those rectangles, they will be the same, okay? So the width of each one of those rectangles is 2/5, okay? Now, because this is a right-hand approximation, okay, we're looking right here at the right hand of each one of those rectangles. The values are 2/5. This one, oh, let me see if I can move this down just a little bit so I have. Move that down. erase some of this. And then we can rewrite it in just a second, guys. Bear with me, okay? The right hand approximation. Bear with me, okay? We've got from 0 to 2, n equals 5, and we've got the width of each one is 2/5, okay? So we divide 2 by 5, and the right hand of that first rectangle is at 2/5. Then that one is at 4/5. That third one is at 6/5. This one right here is at 8/5. And then the last one has a right hand that is at 2. Okay? If we want to find the area, we are going to have to find the width times the height of each one of those 5 rectangles and add them up together. Okay? So we already know that the width of each one is the same. So the area that we are approximating is the width times, we need to get the heights of each one of those right-hand rectangles using the curve. So the way that we'll do that is we will evaluate the curve first at 2/5, because that is where the right hand of that rectangle, of that first rectangle, meets the curve. Okay? So 2/5, which means that this is what we will put into our calculators and get a value. Okay? So you guys are going to be using your second enter thing. Okay? So let's do that. We will first enter in 2/5, store x, enter, and then enter in your function, negative x squared plus 5. So when we evaluate that function at 2/5, we will get 4.84. Okay? The next value that we are evaluating is 4/5. So 4/5, store x, enter, second enter, second enter, enter, and we get 4.36. Okay? Then we will also do that for 6/5. So what this is doing for us is giving us the y value, which is the height at that right-hand side of the rectangle. And then if we did 8/5, store, using our second enter thing, we get 2.44. And lastly, we can see that the height at 2, well, let's just see. So 2, store x, enter, only because I didn't put the y values, I didn't label the graph. That is at a height of 1. Now, what we're going to do is add all of these numbers up inside the set of parentheses and then multiply that sum by 2/5. Okay, so adding up, times, we get an area of 6.48. Okay, that is the area when we have an underestimate. That is the lower sum. Okay, now we're going to work the same, exactly the same idea for the over approximation. This time we're looking for the left height. Okay, so what we are going to notice here is that, and I'm going to get a different color, so hopefully I can bring this to your attention. Okay, over in the right hand approximation, that right hand approximation right there is the same left hand approximation right there. Okay, so we'll notice that in the left-hand approximation, we're going to be using that first left side that we did not use over here. Okay? Likewise, we used that little right side of that last rectangle, and we are not using it over here. Okay? And what that does is it makes our work a whole lot easier. Okay? So the area is still the width being the same. Okay? And we are going to evaluate the left height of that very first rectangle by evaluating f of 0. Well, f of 0 is equal to 5. Okay, so we have the first left height. Now we can pull the next 4 heights from the right-hand approximation. So 4.84, 4.36, 3.56, and 2.44. Okay, we will add all of those up together. And then multiply that by 2/5. And we get that this area over here is 8.08. Okay, you've got an under estimate and you've got an over estimate. Now we're going to add those two together and divide. So 8.08 plus 6.48 divided by 2 gives us an actual area of 7.28. Okay, and I did do some rounding. So anyway. So adding the 2 and dividing gives us the actual area. Okay, now what we're going to do is the exact same process using summation. Okay, so we know that the width of our rectangle is b minus a over n. Okay, and instead of using the 5 rectangles, okay, we are just going to use n for a random number of rectangles. Okay, so in other words, what we're doing is taking the graphs and we are putting in an infinite number of rectangles. So back here we had n equals 5. We had 5 rectangles. Here, when we put in an infinite number of rectangles, then you don't know how many you've got. Okay, you are approaching infinity as far as the number of rectangles that you've got. Okay, now the height of each rectangle. Okay, this is very important. Okay, the height of each rectangle will start at the lower end point, and then you will have the width times I. And that's the formula for the height when you are using n, or an infinite number of rectangles. Okay, so our lower end point there is a 0. Okay, so in this case, our width is 2 over n, and our height is 0 plus 2i over n. So we took the width of 2 over n and just multiplied it by I. Okay, that height there is what replaces x in our formula. Okay, so we've got the sum from one rectangle to an infinite number of rectangles of, so remember, the area of the rectangle is the base times the height. Okay, we're putting in the height first, so negative 2i over n, that's our height, squared, because negative x squared is what's in our formula. Okay, remember, the height replaces x. So we've got negative 2i over n squared plus 5. That's the height. Now we have to multiply it by the width. Okay, so this is the height, replacing the x, and this is the width. Okay, now we're going to get to it here. First thing we're going to do is deal with that squaring. So we've got the sum from 1 to n, and yes, you do have to write this down every single time. Okay, so when we square 2i over n, we will get 4i squared over n squared, and then plus 5 times the width of 2 over n. Now the next thing we're going to do is distribute. Okay, so we will distribute and get negative 8i squared over n cubed. Okay, then we will distribute the 2 over n into the 5 to get 10 over n. Okay, now the next step is going to be to separate those two terms. Okay, so we will have the sum from 1 to n of negative 8i squared over n cubed plus the sum from 1 to n of 10 over n. Okay, now we're going to pull out the constant over whatever power of n we've got. Okay, so for that first term here, we're going to pull out a negative 8 over n cubed, and what we're left with when we factor that out is our I squared. Okay, and likewise, we will factor out the 10 over n times the sum from 1 to n of 1. Now going back to the beginning, this is the point at which we are going to be able to sub in terms of n, what I squared is equal to. Okay, so you will refer to your notes and you will see that I squared will be replaced with 2n cubed plus 3n squared plus n all over 6. Okay, and then you've got your constant summation rule right there. Okay, so plus 10 over n times 1n. Okay, now the next step is to distribute. So we are going to distribute this negative 8 over n cubed into each one of those terms. Okay, negative 16n cubed over 6n cubed. Then we will do negative 24n squared over 6n cubed minus 8n over 6n cubed, and then plus 10n over n. Okay? Now, remembering our algebra, n cubes cancel out and n's cancel out. Now, the thing here is we are actually looking for and I'm just going to write it in here, the limit as n approaches infinity. As n approaches infinity. Okay? So, even if we do some reducing right here, okay, n squared will go away and take 2 of those away. One of these n's, this n will go away and take 1 of those with it. Okay? But if you remember, if n goes to infinity, 8 divided by infinity is 0. So in other words, anytime we end up with no n's in a numerator, but we do have some in the denominator, those are the terms that equal 0. Okay? So what we're left with is negative 16 over 6 plus 10 for our area. So let's see what we get when we do that. And negative 16 over 6 plus 10 gives us an area of 7.33. And that is the exact area under that curve when you use summation. So this is the average of the two. Okay, but look at how close they are. Okay? So using summation gives us an exact area under a curve. Okay? And I believe that's it. All right, so I have to check on the IXLs. Work hard, guys. You'll get this.